As we continue to talk about radicals and exponents in this unit, we're going to focus more on rules for simplifying exponents when they're multiplying. So just to review, the big number is called the base, and the little bitty number is called the exponent. When we talk about expanded form, 5 to the third power means 5 times 5 times 5. And if we wanted to take our calculator and multiply 5 times 5 times 5, it would simplify to 125. You can also put 5 to the third power in your calculator by using the little caret. So when we talk about simplifying numeric and algebraic expressions, in these next two examples, write in expanded form. So we're going to take it and multiply it out, and then express it as a single base. So a single big number is the base to an exponent. So 4 squared means 4 times 4. This is our 4 squared. And 4 to the 5th means 4 times 4 times 4 times 4 times 4. So this is our 4 to the 5th. So now I have 1, 2. Let me change this real quick. So I have 1, 2, 3, 4, 5, 6, 7. I have 4 sevens multiplied by each other. So I have 4 to the 7th power. So when we look, we can also do this with letters. Your base does not always have to be a number. So n to the third is n times n times n. And then I have another n to the third, n times n times n. So when I count them out, 1, 2, 3, 4, 5, 6. So this simplifies to n to the power of 6. So what would be some patterns that we noticed? Well, hopefully we noticed that if I have 4 to the 2nd times 4 to the 5th, if I take and I add my exponents, 2 plus 5, I get my 7, which is my exponent on my 4. And in like manner with my n's, n to the third times n to the third, well, 3 plus 3 is 6, which was my exponent on the n. So our pattern needs to be that we need to add the exponents. Now that only works when that base number is the same number or letter. So the product of powers property says a to the x times a to the y, where these a's are our bases and they are the same, it will stay the same. We're going to just add our exponents, and that big number will stay. So we can apply this. We can say, okay, x to the 5th times x to the 12th. So I usually write my x, and then I just write my rule, 5 plus 12. 5 plus 12 is 17. Now you can write this out in expanded form, but the goal is for you to learn how to utilize that rule. So when these get really large, you don't have to do that. So 4 plus 4 is 8, so 9 to the 8th. Now this b does not have an exponent on it right now. This is a 1, right? So if there is no exponent, it's an invisible 1. So this becomes b to the 1 plus 7. So b to the 8th. Notice all of these have, even though there's 3 of them, they're all the same base of 3. So we're going to say 3 plus 4 plus 5 is going to be 3 to the 12th. And you can always check all of this if it is a number by putting in your original into the calculator and then putting this new one into the calculator to make sure they match. When expressions contain different bases, group powers with the same base. So same big numbers together, and then apply the power rule. So here's what we need to realize. We have 3 times 5. So regular numbers, we're going to have, if we have regular numbers, we're going to have regular math. So what this is saying, I have different bases, so I'm going to write them separately, 3 times 5. And then I have like bases of x's. So I have x to the 4 plus 5. 3 times 5 is 15. X to the 9. So if your numbers are different, you're just doing regular math. We're only doing this addition when the bases are the same. So here I have 4 and I have 6. Those are different. So again, we're just going to write it out separately. 4 times 6. And then I have x to the 3 and x to the 2. So x, 3 plus 2 because they're being multiplied. This y is missing an exponent. I'm going to put a 1 there. 1 plus 3. So 4 times 6 is 24. X, 3 plus 2 is 5. Y, 1 plus 3 is 4. Same thing here. Make sure you're putting the 1s there when it doesn't have it. These are different. These coefficients, these numbers in front are different. They don't have any exponents, so we're just going to multiply negative 2 times 8. And then I have a to the 1 plus 2. B to the 3. I don't have another b, so it's just b to the 3. So negative 2 times 8 is negative 16. 1 plus 2 is 3. B to the 3. Sometimes we have, it says write A, C, and D in expanded form and then express as a product raised to a single exponent. So I want you to notice this is a little bit different because we have a number inside and outside the parentheses. So if we're going to write it in expanded form, this says that I need to write 2 squared, which is 2 times 2. I need to write it 3 times. 2 times 2 and 2 times 2. So when I count that, I have 1, 2, 3, 4, 5, 6 2's. So I have 2 to the 6th power. Same thing here, 4x squared. So I've got 4 times x, and I need to square that. 4x, x. And when I do that, I get 4 times 4. Those are my like bases. And I have x, 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 x. I have 4 x's. So I said 4 times 4 is 16. And I have 4 x's, x to the 4th. So what are some patterns that we notice? Well, I'm hoping you realize that this is just like the distributive property. So we are going to multiply or distribute. We'll put distribute in parentheses because it has parentheses. The exponents. I forgot my E. So what does that look like? That looks like this. A to the x times y. Now remember, we talked about that invisible exponent, right? If you have 2 things inside the parentheses, like we did on letter D there, a to the x, b to the x. And if you happen to, like on this one inside, we had an extra number and letter, so we would multiply them both. So we're going to apply these new properties and simplify. So instead of writing x to the 7 out 3 times, we can say x to the 7 times 3, x to the 21. Remember, there are 1s on all of these, so we need to distribute to everything inside the parentheses, just like when it was regular math, right? So 7 to the 3rd, c to the 3rd, d to the 3rd, because they're just 1s. If you wanted to write 1 times 3, 1 times 3, 1 times 3, so you can see what's happening, you can do that. There is a 1 on this 12. There is a 1 on this c. So we're going to say negative 12 to the 1 times 2. A to the 6 times 2. B to the 5 times 2. C to the 1 times 2. So negative 12 squared. If you wanted to write that out as 144, you could. A, 6 times 2 is 12. B, 5 times 2 is 10. 1 times 2 is 2. All right, so now we're getting a little more complex. So make sure you put those ones. So we're going to say 4 squared. You'll get to a point where you learn the rules and you don't have to write it out. If it helps you to write it out, then do that. 2 times 2 is 4. 1 times 2 is 2. I still have my 2. Only thing inside the parentheses is that y. So 3 times 4 is 12. Now we're going back to what we did on the first side. So I have 4 squared times 2. Well, 4 squared is 16. Times 2 is 32. X to the 4th, I only have one of those. But on my y's, I have y to the 2nd and y to the 12th, and I need to add those. So I get y to the 2 plus 12 is y to the 14. Alyssa believes the following expressions are equal. For any value of b, is she correct? Well, on this first one, this is like the front. We said we had to add them. So this is 4 plus 7. And this is 4 times 7. Well, are those the same? Well, last time I checked, no. B to the 11 is not equal to B to the 28. Which expression, the expression x to the 15, x to the 6 to the 4th is equivalent to x to the n. So what is the value of n? The n is the exponent, so we need to we have x to the 15. We can distribute on this one. 6 times 4 is 24. And now we need to add these. X to the 15 plus 24 is x to the 39. And they're asking about n, so n equals 39. Last two. Sanjay simplified 3x to the 3rd and 3x squared to the 4th as shown. Identify her error. So remember, when we do these, it's always easier for you to go ahead and do your own work. I'm going to put my ones there. So I have 3 to the 1 times 3 and x to the 1 times 3. And then in my parentheses, I have 3 to the 1 times 4 and x to the 2 times 4. So I can simplify these. I have 3 to the 3rd, x to the 3rd, and then I have 3 to the 4th, x to the 8th. So I'm going to put my 3's together. 3 to the 3 plus 4, x to the 3 plus 8, and we get, 3 to the 7, x to the 11. So we can see that is not what she got. So if we look at our steps, her mistake is actually right here at the end, because she ended up multiplying instead of adding, right? But when they're not a power to a power, when it doesn't look like the distributive property, we're adding. This one's a little bit trickier. Area of a circle found using a equals pi r squared. Write an expression that represents the area of the circle with a radius. All right, so here's my r, and leave it in terms of pi. So we're going to leave it in terms of pi. That means we don't have to do the multiplying by pi. Now it says r squared. So in my parentheses, I have 5x to the 7, y to the 3rd squared. So I'm going to put my 1, and we're going to distribute. A equals pi times 5 to the 1 times 2 is 2. X, 7 times 2 is 14. Y, 3 times 2 is 6. And there you go. Now, sometimes it does ask us to go ahead and multiply those regular numbers. If we wanted to do that, you could also write 5 squared is 25, x to the 14, y to the 6, and then they usually put pi on the end. So I would actually take either of these. Make sure you do some work on your practice. Refer back to your notes because the rules can get a little confusing. So pay attention. Is it a power to a power with the distributive property like here? Or is it just where you need to add them like this, okay? Have a great day.